Alright, this video is to go over all the key graphing things you need to be able to do in Kinetics. So I'm going to hit each of the key graphing objectives, and then by the end of it you should know exactly how graphical analysis of kinetics of chemical reactions applies as far as AP. One of the first things you have to be aware of is you have to be aware of when we talk about a calculation of an average rate. What are we doing when we do an average rate? Well, you're basically taking concentrations at two different times, and you're just doing basically rise over run is basically what you're calculating. So if you look right here, for example, you have this data point right here, which is a concentration and a time, and another concentration at another time, and you're calculating basically rise over run. So whenever we calculate the average rate of the reaction is change in concentration, so you have 2 points over basically change in time, and you do the calculation from the graph, just rise over run, very similar to what you would have done anything in geometry. When we do an instantaneous rate of a reaction, we're talking about a single point in time. So we're talking about, like, for example, the instantaneous rate of the reaction at that point right there. That point right there, what you do is you run a line that's tangent to that point. So if you notice the slope of this line right here runs exactly tangent to that point, and then from that you basically can calculate the rise over run and calculate out the instantaneous rate of reaction. So the key difference in an instantaneous rate of reaction is you just have a line that's tangent to a single point. It gives you like a snapshot, like you guys have Instagram, right? This is like an Instagram for rate. It's a 1 second little picture of what the rate of reaction is. So for example, if we took the instantaneous rate, when we always use the initial rate in kinetics all the time. So what we're doing is we're calculating the slope at time 0. So it's basically a line tangent to the curve at a time of 0 seconds. Here's an instantaneous rate at a time of 600 seconds. You see the points right there, and then you calculate the rise of a run using the slope of the line. Here's examples here. Here's an instantaneous rate for that. There's an instantaneous rate right there. Instantaneous rate right there. It's key to remember, because if you look in the AP exam, here they ask you a question. It says, indicate the time at which the reaction first reaches completion, mark in X. So completion means going from kinetics to equilibrium. We haven't completely got there, but once the line goes flat, the line becomes complete, or the reaction becomes complete. It says, explain how to determine the instantaneous rate of formation of I3 minus at exactly 20 minutes. So if I go to 20 minutes, there's my point right there. The way I would figure out the rate, they don't actually have you calculate it, but you explain how you would, is you would calculate it using the slope of that line at that's tangent to that point on the graph. And that's what they're asking you to do when they ask you for instantaneous rate of reaction. The next thing that comes up a lot of times is you've tried to find the order. We learned the sandwich method to find the order. We learned the mechanism based on the slowest step. There's another way to find the order of a reaction using a graph, actually. It's called finding a reaction order by a straight line plot. And what it is this is three situations you have to kind of commit to memory. You want to sketch these in your notes right now. A zero order reaction, if you take a zero order reaction, you take the concentration of the reactant A, and you have time on the bottom. Notice all these graphs are similar because time is always on the bottom. The difference is what's happening to the concentration of the reactant. This is just the concentration, this is the log of the concentration, and this is the inverse of the concentration. What happens is you plug the data into a graph or Excel. You won't actually have to do this, but they'll show you graphs. I'll show you what they mean in a second. And what you have to do is identify which one gives you a straight line plot. Now these would be different this is for a zero order, this is for a first order, this is for a second order. Notice in a zero order reaction you get a straight line plot when A is the concentration of just the reactant is on the Y. Notice also that you can tell the K is equal to the negative slope of the line. So the slope is equal to negative K. In a first order reaction, if you have log of the concentration of the reactant A, you'll get a straight line plot. Slope again is going to be equal to negative K. In a second order reaction, if you take the reciprocal or the inverse of the concentration of A, you get a straight line plot that looks like this, and your slope is actually equal to K. So whichever plot gets you a straight line is the easy way to determine the order. The data values will be presented three different ways. I'll show you what it looks like here. Here's an example. Let's say they give me the data. Here's the time, they give me B, they give me the log of B, and they give me the inverse. What they'll do on the AP exam is they'll provide me 3 graphs. You have to basically identify the graph with a straight line is all you're doing. It's kind of like Where's Waldo, except in this case, what you're looking for is you're looking for a straight line plot. Bam! I have a straight line plot right there. What is on the Y? B is on the Y. If I go back, when the concentration of just the reaction is on the Y, that means this would be considered, this reaction that I know to identify is a 0 order, whoops, that's not the right pen. We would say this is a 0 order reaction because I get a straight line plot when the concentration of the reactant only is on the Y. Here we have another situation. I have A going into products. I have a data table. I have A, log of A, and the inverse. What they'll do on the AP exam is they'll provide me a set of 3 graphs. So I have 3 graphs, and I find the straight line. Boom. This is my straight line plot right here. I look and see what's on the Y. I have the log of A. Well, if I go back to my initial chart, memorization-wise, whenever I have the log of A on the Y, it tells me that it's going to be a first-order reaction. So I come over here and identify this reaction, and that's all they're going to ask you to do on the exam is identify this would be a first order reaction because that's what gives me a straight line plot. Next one, I have C, concentration, log, inverse. Take a look, I look at the data. Well, regular concentration of C is not a straight line. Log of the concentration of C is not a straight line. Bam, right there, I got a straight line. What is on the Y? 1 over the concentration of C is on the Y. When I go back to my chart we initially started with, whenever you have the inverse on the Y, it means, and you get a positive, or not a positive, if you get a straight line plot, you know then that it is a second order reaction. So if I look right here, I can identify this as a second order reaction. And that's all you have to be able to do. Here's an example right from the AP exam. Given the reaction here, order is 0, 1, or 2, use the information on the graphs to correspond to the following. So they give you this reaction right here, and they give you these plots. If I notice, as soon as I look, I see a straight line plot right here, then I know that automatically I know that it has to be a 0 order reaction. It's a 0 order reaction, so it says determine the order of the reaction with respect to ethanol. So I know it is a 0 order. How would I justify my answer? Because the fact is the concentration of the reactant on the Y gives me a straight line plot. If I had to write a rate law, I would write rate is equal to K, because there's nothing else in there because it's a 0 order reaction, right? So you see that. Here's another example of a chart they gave me. In the AP exam, they gave this chart and said, hey, which one gives me a straight line plot, right? So if you look right here, the inverse does not, the concentration of X does not, because it's not 0, it's not second order, it's got to be first order. In this case, it would be a first order reaction because of the plot. Okay. Next thing, energy diagrams. We've seen these before. We saw these in endo and exothermic reactions. An energy diagram has the potential energy listed on the side. You always have the reactants on the far left, products on the right. What you want, key things now that relates to this chapter is we talked about activation energy is the amount of energy required to start a chemical reaction. So activation energy on this graph is represented the distance between the reactants and the top of the hill right there. That represents activation energy. The distance between the two lines, the reactants and the products, is the energy change, or in thermodynamics we said it was delta H for the reaction. You can find it off the graph that way. So this is an exothermic reaction because the energy is dropping or leaving, so the delta H is negative in that case. If you look, a key other thing you have to be able to understand in kinetics is we start with the reactants, they slam together. What happens is you start with you have a reactant here, they slam together and they make what's called an activated complex. That's where all the bonds are kind of broken, or the bonds that are going to break in a reaction are broken. So the activated complex is always at the top of the hill. Has enough activation energy, the bonds have been broken, ultimately they'll form products. Activation energy is key in this chapter is the energy barrier, or the hump that must be overcome for a chemical reaction to proceed. That's why they need a certain amount of kinetic energy when they slam together for an effective collision, is the amount of energy to basically make something happen. It's kind of like if you were playing golf and you were putting, right? You have to hit the ball hard enough to go up over the hill. Otherwise, it won't make it all the way over. It wouldn't make it all the way over here. So that's what activation energy is. The activated complex or the transition state is at the top. So the activated complex is when you're up here. This is an exothermic potential energy diagram. You can see it right here. We have the reactants, you have the products. The activation energy for the forward reaction is from where you start to the top of the hill. If you were doing the activation energy for the reverse reaction, so starting with the products, going back this way, this arrow would represent the activation energy for the reverse reaction. This one from the reactants where you start to the top of the transition state represents the forward reaction. An endothermic potential energy diagram, notice the products are at a higher state than the reactants. You still will have an activation energy line. In this case, the activation energy is fairly large. You can also determine the heat of reaction from the difference from the one level to the other. So we would say the delta H is here, and it's positive because over time it reaches a higher amount of energy. Here's the example when we talk about catalysts and how they speed up a reaction. They produce an alternate pathway. So this is the normal hill, right? So this is the normal hill. Like whenever you catalyze something, what you're doing is you're lowering the amount of activation energy by an alternate pathway. So this is the new activation energy. This line would represent the old activation energy. So whenever you add a catalyst, what's happening is you're basically decreasing the amount of energy required to break the bonds. We've already talked about this. This is an exothermic reaction because over time the energy is dropping. This one is an endothermic reaction. Key things that we've discussed in this chapter, really we focus on mostly just the first order. You need to know, first of all, this is a different form of the integrated rate law, but it's the same thing we've been using in class. You're not responsible for the integrated rate law for the first or second. We talked about the straight line plot. That's what I showed you. You can determine, depending on what's on the y, this is the exact same thing I was showing you. You will get a straight line plot. Slope of k, when you graph it, if you get a straight line plot, k is equal to negative. Slope is equal to negative k here, negative k there, positive k there. Half-life, the only half-life you're responsible for this chapter is 0.693 divided by k is equal to the half-life. Last thing that they do ask about is, we know that temperature increases the amount of a reaction rate. The reason why is because a higher number or a higher fraction of molecules will have a greater amount of kinetic energy. As the temperature increases, more molecules have enough energy to slam into each other and have something happen. So let's say we took an activation energy. This is the line. This is like 90% for passing, let's say, for a test. 90% to get an A. If my test average down here is like 56, only a small amount, that small fraction of molecules, if my average is way down here, let's say if my temperature is 56 here, if my temperature goes up to 75, that means when the temperature is a measurement of the average kinetic energy of the molecules, if the average is here, that means more of the molecules have the required energy to break the activation energy. And then let's say if my average was like a 95, the majority, look at the majority of the molecules have the kinetic energy necessary to break the activation energy barrier. This is called the Maxwell-Boltzmann distribution. It just says at higher temperatures, you know more molecules have the adequate or enough energy, activation energy to react. That's why the reaction rate increases, because you have a minimum energy required for a reaction to occur. So what happens is as you increase temperature, more molecules, you can see the difference between the red and the blue here, more molecules have the required amount of kinetic energy in order to cause a reaction to occur. And that's really what happens. That's the justification for increasing temperature and how it increases reaction rate. And they would expect you to be able to explain it or use this graph as well. All right, hope you guys have a good rest of your 3-day weekend. I will see you on Monday.